present about Qniverse. And I'm also proud to say that we are one of the collaborating member in his technical group in National Quantum Mission. And since Professor R.P. Singh is there, uh, this tool that I'm going to talk about is about on Qniverse. But he has helped us in developing one tool called Quantum Network Simulator. So the results that he was showing in the paper, those were the results that we took as a reference for building that simulator and validating the simulator. Thank you very much, sir, for supporting us for a long time. We have been disturbing him for a long time on this tool. And I think I will get an opportunity to talk about quantum network simulator sometime, probably in the next conference where we will have the tool publicly available. So right now, I'll speak on Qniverse. Like Anirban said, this is a bit different talk altogether. I don't know whether it fits in this conference. Last 2 days, you have been hearing on many research-related topics. Like my head was revolving when I was hearing all these research-related topics. But nevertheless, this tool will help you to carry out such researches, at least on the quantum computing side, okay? So the Qniverse name was interestingly defined. He made it very simple, replace U with Q, right? That is what we did, but later we tried to justify why we did that. So we wanted to build a platform that will be an umbrella platform that will allow you to access the n number of quantum computing simulators that exist in the market. Not only you run that on a CPU platform, you should be able to run that on GPUs, vector processors, and FPGA platforms as well. And then the same code should be able to run on the quantum hardware. When I say quantum hardware, it is not just the superconducting-based system. Though you design your circuits using a gate-based system, you design for a gate-based system, we will take care of transpiling that into a photonic system, or a neutral atom system, or an ion trap system. So we wanted to have a one platform. Say, let us say that you are a researcher who wants to develop a new drug, right? What is that you are bothered about is developing an algorithm or a use case that runs and gives you the desired result. You are not really bothered whether it is going to run on a superconducting system or a photonic system, right? And you need not learn different languages for running these algorithms on different platforms. All you need is just stick to one way of writing your quantum circuit or an algorithm, and we will take care of transpiling that into a format that is required for the hardware. So that is how the Qniverse was started. I think I will not speak about the potential of quantum computing. You very well know that. That's why you all are here, right? But this is an interesting picture that I got it from a McKinsey, which is pretty old. Nevertheless, it's a very valid one. So here, this picture talks about the various stages of the quantum system, the noisy systems that we are, in the NISQ era, the systems that we are talking about. And then the next stage is going to be fully error-corrected systems. And then the universal quantum computers that will solve most of the real-world problems, right? So these are some of the problems, which I will not discuss in detail. However, if you have to make any breakthrough in these application development, if you want to solve these problems, what is that we need to do? Can we make it interesting or interactive? We need to write algorithms, right? So that is the challenge that we have. We need algorithms, or we need algorithms that are equivalent to the classical algorithms that exist for various problems, right? But building these algorithms is not that easy. It has various challenges. Though the mountains are of varying sizes, it does not really mean that a particular challenge is very high and another one is very small. But what it means that there are plenty of challenges if you have to develop an algorithm, particularly if you are an algorithm developer and if you want to learn quantum computing. The first one is, when I get into the field of quantum computing, I see there is a diverse qubit modalities that is available in the market, right? There is a superconducting system, photonic system like Dr. Chandrasekhar is working on, and then neutral atom systems, NMR, NV centers, ion traps systems, right? But I'm not really bothered about all these systems, right? I just have a problem, and I want this problem to be solved, right? And each of these systems behaves very differently. It works very differently. If I have to run an algorithm on these systems, I have to learn some native packages, native programming languages, how I have to write those algorithms, right? The other one is that lack of standardization. So there is no the standardizations are still evolving. We should not be blaming that. There are many standardization working group who are working on building a common way of writing your algorithms, right? But we thought we should come up with a platform where you design your circuit once and then run it on multiple hardware. Similarly, run it on multiple simulation frameworks that exist in the market, right? And then lack of interoperability, right? CDAC is being known for high performance systems. We build supercomputers. We have been doing that for many years. We have been running many real world problems that are solved using the supercomputers, like maybe a CFD application or weather forecasting. But we always believed, even though the quantum computers exist, any meaningful applications will be hybrid in nature. So it becomes very important, how do you integrate this HPC system with a quantum system? So how do you run your hybrid applications using the Qniverse platform? So we have that particular module also handled in the platform. And then I'm a computer science guy. I know how much difficult I have gone through in understanding the basics of quantum computing. I still say that I understand only the basics of quantum computing because my colleagues, Dr. Naresh and Mohit are there, who are the real quantum researchers. So learning quantum computing is not straightforward, at least for the classical people like me. So that is a big learning curve. And this platform will help you to speed up that particular process. So that's the reason before building this platform, we wanted to run a small survey. Okay, so we floated this survey across social media platforms. And we wanted to identify whether there is really a need for such unified platform. Whether the users are pretty happy with whatever platform that exists in the market, or they are expecting something new. So this is what the results that we got. How important it is for a single unified platform that integrates all the quantum computing systems in one platform. So you can see the result that 78% of people felt that we need such platform. Similarly, we asked, what is the biggest challenge that you face? One is the talent and the knowledge resources. The knowledges and the resources that are available in the market are scattered. How to bring them in one place? And the other one is the hardware constraints. Not all the machines are available for a cheaper cost, right? You know that you have to spend $48 per minute for accessing an IBM quantum system, right? So how do we get that system here? And similarly, there are many systems like a strawberry field. Xanadu has a photonic system, like ion trap machines from IonQ. So how do we get all these systems into this? Okay, so that is the motivation behind developing this particular tool. Sir? This was around 300 people, sir, who participated in this survey. Yeah. So I like this particular quote from Winston Churchill. It says that out of intense complexities, intense simplicities emerges, right? So I talked about the various complexities and challenges in building a quantum algorithm, in understanding a quantum computing as such. So that is the motive behind coming up with a simplified platform that is called as Qniverse. You can access this platform in the domain qniverse.in, okay? I'll show the demonstration of it. So it's an integrated platform for designing, simulating, and executing quantum algorithms on classical accelerators. As I was telling it, you can run it on a GPU so that you are able to simulate more number of qubits. At present, you can simulate up to 35 qubits. Beyond that, it is not possible on a classical system. And we are exploring on having this FPGA and vector processors. We don't have that in the platform right now. We are not getting a much better improvement in increasing the scalability of qubits, but it can solve some pretty good problems. And behind this platform is the quantum development kit, just like you see Qiskit and Cirq kits. That is the brain behind this kit, which provides all these features that we saw in the Qniverse platform. So this is the simple architecture of Qniverse. So once you access the Qniverse platform, you get a layer where you can design your circuits visually. You can drag and drop the gates, just like you have been doing in IBM Q experience, right? You can build your circuits. And this circuit is translated into an quantum intermediate representation. We call it as QIR, okay? So it gets translated into a QASM format. And this QASM format is given as an input to a transpiler, okay? The quantum transpiler job is to take this gate-based circuit, and if I want to run it onto a photonic system, how do I transpile this into an optical circuit, right? If I want to run it onto a different simulation framework other than Qiskit or a Cirq or a Penny, how do I get this translated to that, right? And we also have some preloaded algorithms which you can click and load those algorithms and get started with. We have almost 30 algorithms. Some of them are which are existing in the market, including Professor Anirban's veto algorithm, which is present there. He talked about it in one of the seminar as well. And then we also have various simulation framework. The photonic simulator is something that we are working with Professor Chandru in the National Quantum Mission. So CDAC is developing the photonic simulator. We should target at least 24 qubit. We should be able to simulate on the classical system. We have already done up to 6 qubit. We have demonstrated to him to take his feedback as well, but I don't have it in the platform right now. It will be in the next version. So we can add more such frameworks here. And once we have this transpilation done, we do a bit of an optimization so that it gets run on the quantum hardware and also gets optimized so that it runs on the parallelized platforms like GPU, right? And at the back end, we have the HPC systems. So we have a Param Utkarsh high performance system at CDAC Bangalore. We have one Param Shakti in IIT Kharagpur. So these are the systems that has been integrated. So all of the classical accelerator sits behind that. So if you choose to run it onto a simulator, it gets run on the supercomputers, right? So that you get at least 30 to 35 qubits. And we have a simulator called QLAX, which supports up to 40 qubits as well. And if you have to run it onto a hardware, we have a couple of approaches. One is the loosely connected approach, where we connect to the quantum hardware that are available in the cloud via an API. Another one is the direct integration with the hardware. So at CDAC Bangalore, we'll be having a 100 qubit superconducting based quantum system. Tomorrow is a very critical day, or the next week is a very critical day where we are announcing who is the winner of the tender who will be setting up this machine. So we'll have this machine readily available in 9 months' time. So that gets integrated here, so that will be a tight integration. So whatever I have done now is with IBM Quantum, we have integrated as a loosely coupled system. And we have integrated with Quantum Inspire, which is a Delft consortia, which has a Starman 7 and 5 qubit machines. So those machines have been integrated. And the orange box that you see is the NQM hardware. So when our 48 qubit photonic system is ready by Chandru, we will have that system integrated here. Yes, sir? So it is not a target that I'm setting. I'm just so eager to see that system and gets integrated to this platform. And he has helped us to set up a 6 qubit photonic system in CDAC Bangalore. So we are in the process. Once that is ready, we will test it with that first before we come to you for the 48 system, right? So this is how the architecture looks. And as I was explaining, it is an unified platform. So you all need to do is design once and run it on multiple frameworks. Quantum SDK is the one that enables all these things. And then we have some algorithms which are optimized so that you can kickstart your development from there. And hybrid HPC quantum is a complex integration that we have enabled some of the VQ algorithms that you can test here, variational quantum eigensolvers. And it also provides a comprehensive learning ecosystem. So why Qniverse matters? It's like a product pitch, right? So as I told. So it helps you to develop algorithms with a reduced development time, and it provides a simplified hardware access. It also comes with a very good debugging facility, where you develop your algorithms before you run it onto an expensive quantum hardware. You run it onto a simulator, test those, introduce some noise parameters, and mimic the quantum hardware, see the results, modify your quantum algorithms, and it is now ready to run on a quantum hardware. So that's the idea behind this. So code once and run it on multiple platforms. And it accelerates the learning curve. So before I get into the demonstration, I have around 5,000 users making use of this platform. So I have given it to many people and asking their feedback on how this platform is. So here are some of the feedback that we have got. And there have been some people talking about us in various forums as well. Right? So as I was explaining, Qniverse is designed to balance performance and accessibility, enabling users from diverse backgrounds to engage with quantum computing effortlessly. So the one that I have circled suits me because I am from a very different background compared to the people who sits here, right? So these are some of the publications that we have done, and these publications have primarily used Qniverse for testing the algorithms. And we have cited Qniverse over here. So I see many researchers here. Tomorrow, if you make use of Qniverse, you will make use if you try once. And if you like the platform, if you have carried some research and publications, please cite us so that it will help us to reach many people, right? So with this, if you have any questions, you can write it to me. I handle the quantum technology group in CDAC Bangalore. We have two different groups, one which works on the hardware, the other one which works on the software for the quantum systems, right? So you can write to us, and this project is funded by Ministry of Electronics and IT. So I'll go to the demonstration without delaying. So I'll take a chair because I have to type few things. So you can access this platform in qniverse.in. Okay, so the page that you see is pretty much a marketing page. We talk about what is this platform is about, like my slides. And it also says that what are the various features that we have here, okay? And then a pretty good video which explains about how this platform actually works and what is the benefit of using this platform. And don't get fooled by this in the mind that when we have 48 qubit system that we will integrate into this, right? So if you want to access this platform, it is free. You can directly go here, register with your valid email address, and validate your email address. You should be able to access this platform immediately. So I will log in. So here, I will just briefly take you through the layout of the platform. If you have used IBM Q Experience, it might look similar to you. So there is a composer, okay, that will allow you to drag and drop various gates from the gate palette over here. We have grouped the gates like a single qubit gates, and then we have some multi-qubit gates, and then we have some building blocks, right? For example, QFT is one of the building blocks that you will primarily use for building other applications, such as shorts or quantum phase estimation, right? So you need not build a QFT circuit. It is already available. You just need to drag and drop as like a Hadamard gate, right? And then you can manage this by creating how many number of quantum registers and classical registers that you need, okay? And then there is also code editor, which I was talking about as a transpiler. So once you build your circuit over here, the code gets created automatically over there. And if you're a good coder, you want to code, then you can code there, and the vice versa happens here. You will get the circuit displayed over here. And then we have some instant probability distribution. So when I drag and drop a particular gate, let's say I wanted to drag and drop a Hadamard gate, right? We know that it plays the qubit in equal superposition of 0 and 1. You get the instant probability. You need not simulate anything, right? So we are able to do this up to 6 qubit, because beyond that, the computational resources is too much, and you don't get an instant probability. I cannot call it as an instant probability that time. So you will be able to do this for up to 6 qubits, but the circuit you can obviously design for more number of qubits. And then it also tells you what is the phase distribution if you have any, right? For example, if I want to show some phase distribution, I can just show it in a different color. So what is the phase angle? So you get to see here as well. And if you're a beginner, I don't think most of you are here are experts. So, but if you're a beginner, there is a pretty good explanation given here. If I choose a particular gate, what is the input and what is the output that you're going to get, and what is the phase value that you will get. So when you click here, you will be able to see that different phase values, right? And then once you are done with the circuit, all you need to do is click this run button, okay? So when you go to the run button, there are multiple options here. You can run this onto a various simulation backends. So what you see in Qiskit, there are multiple simulation backends, a state vector, density matrix, matrix product state, things, and including QSIM simulation framework. And similarly, Circ simulation frameworks are available, right? And you can also choose to run it onto a GPU platform where we have integrated with NVIDIA's CUDA Quantum. So the same circuit can work here. It takes care of the parallelizing things. And when you want to run it onto a quantum hardware, we have an IBM quantum hardware, but the recent change in the IBM platform, the policy change, okay, so we have disabled it right now. But nevertheless, we have something called SuperStack, where you will have an IBM emulator at least available. So we have an ion trap system and as well as riggedy system. So it will take some time to load that hardware. Yeah. So we have IBM Brisbane machine, Kingston, and then Pittsburgh, and I have a riggedy Anka, which is an 84-qubit machine as well. And if I go to the Quantum Inspire hardware, we have one emulator over there and then two physical machines, which is the Starman 7 and Tuna 5 machine. These machines are from a Delft consortium, right? So how do you get these integrations done? What you need to do is you have to go to a profile page, okay? So here I have a place where you can insert some of the API keys for the various hardware, right? So I have the API key for the SuperStack, which is the third party who is providing us those hardware, an IBM key, and as well as Quantum Inspire, right? You can just click on this help page, you can get the API key from the platform, and you can save it over here. Once you are done, don't forget to update your profile, right? So before you get started, you wanted to have a look at what are the various resources that we have. So all of the simulation frameworks that are there, what is the capacity of each of these simulators? So you can see that a Quasar simulator, which can simulate up to 29 qubits. What are the basis gates that are supported by the simulator? How many number of shots that you can perform for your circuit? And similarly, a state vector simulator, right? You can also get more details by clicking on this platform, which talks about all the gates that is supported, right? And also on the NVIDIA Quantum, so we can support up to 33 qubits. You might be hearing that NVIDIA can support some 50 qubits, 60 qubits in a classical system. Never believe that. It is not happening, right? So we have tried across multiple GPUs as well. The maximum that we are able to do is 35 qubit across GPUs, right? And then these are the machines, the hardware machines, the spin quantum computer, and as well as the Starman quantum computer and the Tuna quantum computer. You can also get to see what is the configuration of those machines, and then what is the topology of that particular. So here it is just a 2-qubit system. Probably I'll go to Tuna. Yes. You can see the topology of how the qubits are connected here. And the interesting part of this platform is, here you can see the qubit 0 is not connected to qubit 1, right? It is connected via Q2. Now, when I design my circuit in my platform, in the Qniverse, what if I try to create an entanglement between qubit 0 and qubit 1? Our transpiler takes care of understanding what is the topology of this machine, and it brings the particular qubit next to each other so that you will be able to perform an entanglement. So that's what I was talking about, a transpiler. Now tomorrow, when we have to integrate NQM quantum machines, each of them will have their own qubit connectivity, right? Their topology is going to be entirely different. So this platform, all you need to do is we have a transpiler function which takes the coupling map as an input. It understands the topology, and whatever circuit that you build, it directly translates to that particular hardware, okay? So probably I'll show IBM's topology, which is very complex topology, right? So you don't see all the qubits are connected to all the qubits here, right? So when you design a circuit, you have to be really careful where you are creating these entanglements, whether the qubits are connected or not. That is the worry that as a developer, you will not be taking care of, right? So we will take care of doing this transpilation. I can show one machine that has fully connected qubit, probably I think Starman 7, yeah? Not Starman 7, then probably an emulator, which, yeah. So this is a fully connected qubit, right? So irrespective of what kind of topology you have, this system takes care of it, right? So this is the page that you might be interested, so I thought I'll show you. Now I'll go to the composer. Probably we can create some qubits. So I have a Hadamard gate over here, so you know that it shows the instant probability here, right? And if I want to build a Bell state, right, I drag and drop the C0 gate. The pretty interesting thing is each gate can be edited for changing some attributes, okay? So Hadamard gate, we can only put them into a different qubit. If I want to place this in a different qubit, I just say that, place it. But if it is a multi-qubit gate like C0, you just click this, and then I can add on what is my control qubit and what is my target qubit, right? So I can just change this So this can be the target qubit and this can be my control qubit. So you can create a Toffoli gates by modifying this, right? And then, so let us delete this. And we also have a U3 gate. For example, you know that any unitary matrix should be able to be represented using U3 gate, right? So you can create a single qubit gates by editing, and you can give these theta, pi, and lambda values to create various gates. For example, I will just try to remember. Or Naresh, you help me if I'm doing wrong. Pi 0 pi should give me a NOT operator, right? So you can, instead of using a NOT operator, you can directly modify this U gate, and you can do that. Probably if I have to set a Hadamard gate, I think I have a help here. So I can just click this. It should be pi by 2, 0, and pi. So you can see that it represents a Hadamard gate, right? So you can play with these gates. You can perform various operations. So this is the building block that I was talking about. So this is the QFT. You all know that the QFT is made of multiple basis gates, right? So these are the gates that makes up a QFT. So tomorrow, if I want to build a source algorithm, and QFT plays a key role, I need not build my QFT using these gates. It's already readily available. Similarly, we also have a quantum phase estimation block as well, which you can use it here, right? You can also increase this to multiple qubits, provided I have more qubits. So let us say that I can have 5 qubit. I can go here, edit, and support all these 5 qubits. So I will have a 5 qubit QFT readily available for me, right? So these are the gates that is required for making a 5 qubit QFT, right? So it becomes simple for you to get started with, right? Sorry, sir? You have to go to this gate, sir, and click on the edit icon. You get to know which are the qubits that you have to expand this QFT to. So for that, you should have the qubits created. So you can go to manage and create number of qubits. So for example, if I say it's only 3 qubit, then I can have a qubit. It is here. It is here. This is here. Yeah. Okay. So now, let me go to some of the preloaded algorithms. You will find Professor Anirban's algorithm as well. So we read his paper, and Dr. Naresh translated that into a code. So we have that algorithm here. I think he is the right person to speak about it, but I will just say that I wanted to simulate a Grover's algorithm, and my winning state is 101. Right? You get the circuit loaded here. Right? You need not sit and write a Grover's algorithm. Right? You can see how big the circuit is, and it gets increasing when you have more number of qubits, right? The pretty interesting feature here is you can enable debug option here, and you see the instant probability at the bottom, right? So that shows the initial state of a qubit. I just need to slide at the end of placing all the qubit in the superposition state. What is my instant probability? You can visualize it here. And what is the state after the oracle? 101 is the input to the oracle. So what is that? So you can drag and understand what is the present state of my algorithm. So I got my winning state even after the first iteration, right? So we are talking about 3 qubits, so I have to perform 2 iterations in the Grover, right? So you can do that. And if you want to simplify this circuit, you can actually group these gates. All you need to do is just drag this, okay? I have dragged the barrier gate as well. So just drag it here, click on this, and I will call it as oracle. So this is the oracle of my Grover's algorithm. So I'll say that it is a 3 qubit oracle, right? It gets saved over here. So this is the place all of my custom gates get stored, okay? Similarly, I have the diffusion operator. So I just select this, yeah. Yes. So I call it as diffusion operator. Probably I'll call it as a 3-qubit diffusion so that I can use it later on. Okay, so now I have a very simplified single iteration available with me. Now I don't require all these things, right? I need a measurement, so I'll just leave it. Okay, now you get a lot of space to work with, right? When you have a larger circuit. I know that beyond you cannot deal with 500s of qubits, but it's a good platform to start your writing your algorithms with this. So now all I need is, I just need to have one more iteration performed. So I choose this, expand this to multiple qubits. I have my oracle for the next iteration. I have my diffusion operation for the second iteration as well. So this is how you get to see the instant probability for this algorithm, but we will run that, okay? So I go here, I can choose any of this simulator. Probably we'll choose the Quasum simulator, and then I submit. So this job gets integrated with the high performance system. So you get the job ID from the Slurm scheduler, right? It's a classical job anyway, yeah. So you can click on this. So you get to see details of this algorithm. It is still in the running state. I just need to give a refresh. And my job, I asked for a winning state of 101, and what you see over here, right? And if you have any errors, it gets displayed over here and the status of the job. And you can see the circuit that I used for submitting and the corresponding quantum intermediate representation, the Quasum format, okay? And then this code was run using the Qiskit Quasum simulator, so the transpiler has transpiled the code into a Qiskit code. So you get a Qiskit code as well here, right? So now I'll go here. So probably what I can do is, so I was talking about this, when I place a Hadamard gate, you get to see the intermediate representation here. I can also put an X gate on this qubit. So when I do this, yes, you get an X gate, right? You can convert this code into any format. I want it in a Google Circ format. It is readily available. You need not write a code, right? Becomes pretty helpful when you are writing a bigger circuit, right? And it also gives me the format for QLAX. This supports up to 40 qubits, this particular simulator. And if I am a very good coder, I don't like to use the drag and drop builder. You get a visual editor where you can start editing your code, okay? Unfortunately, for the code that is being edited here, we are not able to translate that into a circuit. So we don't get a visual circuit here, but you should be able to write a pretty long code. Even if this is not enough for you, we have a Jupyter Notebook integrator. So this Jupyter Notebook still simulates on a high-performance system. So you can write your larger codes there, get to see instant output for every statement, and then you can simulate it onto our high-performance systems. Right? Probably we can try one job in Tuna machine if it is available. Right? So probably I'll try an entanglement circuit. Okay, and then I'll add a measure gate. Yes, right. I only need 2 qubits. Okay, and then I'll go to run. Go to the quantum hardware. I'll choose the Tuna machine, right? And I submit the job. I have been facing problem with this machine from morning. Yeah, looks like failed to submit the job. You may have to refresh the window. Okay. My API key must have expired. So I go here. I will refresh my token because this system is pretty serious on its security. They don't give you key for a longer duration. So I just need to confirm. It gets connected to the Quantum Inspire system, right, by TU Delft. I connect this. Yes, yes, set. Update the profile. Okay. I'll go to the composer. Okay, so the job got submitted. So we got the result from the real quantum hardware, right? So you know that we are supposed to get the state 1, 1 and 0, 0, ideally, if it is running on an ideal simulator without any noise. We run it onto a NISC machine, right? So we expect it to have some errors. So we have some probability distribution in other states as well, okay? So now, if you look at, I'll go to a new window. I'll just revisit the topology of. Yes. So we created an entanglement between Q0 and Q1, right? But ideally, it should not work on this machine. Even if you go to a Quantum Inspire platform, you should be aware of how the topology is, and you have to create only an entanglement between Q0 and Q2, or Q2 to Q1. Okay, you cannot create between Q0 and Q1. But this transpiler takes care of doing that job. So how do we do that? We just swap, right? Yeah, transpiled code. Yeah, we just add a swap gate over here. So we get the swap operation done so that we are able to create the entanglements, right? So this is the transpilation part. And imagine that how many such operations that we need to perform if it is an 127 qubit of an IBM or 157 qubit of an IBM, right? They are differently connected, okay? So that's what we take care of. And probably I can show one more algorithm. So you can explore these algorithms later. I don't have much time. Even was speaking of, I think this is not working, Mike. It's working? Okay. Professor Anirban was telling there are some basic algorithms. You can start with Deutsch-Dosso algorithms, Bernstein-Vazirani algorithms, Simon's algorithms, right? And you can also see some quantum machine learning is one of the major. We isolate multiple. Dummy data. Some machine learning algorithm. Oh, it is not working, and I have been speaking, thinking that it is. Okay, fine. Sorry. Okay, so you get to see the raw results as well. I am not an expert in quantum machine learning, so I will not get into the details of this particular output. But if you want to connect with us, I can get connected with Dr. Naresh and one of my colleagues who is working on machine learning, right? So this is something that I can show. Did I miss anything, Naresh? Yeah, I missed something, yeah. So there is, today, I cannot develop any tool that does not work with AI, right? So I need some chatbot here. So if you want to ask some questions to the chatbot, you can very well ask that. Like, what is the status? My last job. Okay. So it says that you submitted K means the last job and it has completed. Okay. It also says that in which cluster you have submitted or which hardware that you have submitted. Okay. You can also ask some custom questions like my last job you. Okay, you can also ask some basic questions of quantum. You will get all the answers over here. You can ask what are the hardwares, quantum hardware that are available. This chatbot runs pretty fast because we have integrated with a couple of GPU servers at the back end, right? So you can use that. And as I was explaining, if you are someone mad about coding, Jupyter Notebook is the one for you. It gets instantly loaded onto some high performance systems so that you will be able to write your code and run it onto an HPC systems, right? And we try to have a good amount of documentation, but I don't know. We should try improving it in many ways. We will take help from professor like Anirban and all. So we have some of the basic things and also have some algorithms as well. And each page will have an explanation of how these algorithms are need to be created in the platform, how you can run, and a bite-sized video which explains how these are created, okay? The one thing that I forgot to explain is the credits. So by default, the platform is free, okay? You get up to 150 credits when you register for the platform, and it gets debited when you start running some jobs, okay? And if you are a very serious researcher and if you are working with Chandru sir, Anirban sir, don't mind, I can give you the credits anytime without any charge, right? But you have to be from them, right? So we will be adding more such hardware in the future, and it involves some kind of an expense. So we are planning to introduce a premium package as well, because the idea is to have as many hardwares as possible. So the next time, probably the next TQC, if at all I'm invited to give a talk, I should be able to have a photonic simulator. I should be able to have a 6-qubit photonic system that uses Chandru sir's approach, right? So with this, I think exactly at 4:30. Yeah. If you have any questions, I can answer. Yes, sir.
Why should it be charged? It's the government of India's initiative to some extent, and whole idea of one of the reasons which we thought when we were planning. Okay, not just as a question here. So when we were planning tutorial session for TQC,
Yes.
I was also discussing with Anirban. Our idea was that okay, I mean, it's a very short time, and what all we can cover, starting from Anirban's, Manik's foundational problem to the end where RP discussed about experimental setup and simulators. So we wanted to cover the spectrum, foundations to sprint, and this is something which we thought or we think, a replacement of Quizquit which students are using.
Exactly.
And across India, a lot of students should get an access.
Yes.
Where universities are having now quantum computing syllabus. It might be very difficult for everybody to understand and explain algorithms. It becomes easier. But if you are putting limits like this, it becomes very difficult.
Sir, the platform will stay as a free forever for limited credits. So when you register for the first time, you get 150 credit, and you get a top-up of 30 credits or 50 credits. We haven't decided on that model. That will get updated on every month. So every month you will have a 50 credits, which you can use this platform for simulating it. So that is freely available.
You have a minimum forever.
Yes, minimum
beyond
facilities.
That usage, you need to okay.
Yes. The reason is, sir, we have been approached by some of the quantum startups like Qniverse, Qnu Labs, all those people. They wanted to use it for a commercial purpose. And we can't just give the platform for it because it runs on our HPC systems. And our HPC systems, which is deployed, it is given for some MSMEs. We are making money out of that HPC system.
I think that point, I think Anirban was also mentioning me some time back that the number of users Qniverse now has is very impressive.
Yes, we have 5,000 users. Yes,
and that's what makes it promising to take things forward.
Yes.
With the imposition of all the restrictions
these
days, right?
Yes.
So everything indigenously developed will be very useful.
Yes, sir, it will be staying as a free. One challenge that we faced is when we want to integrate with Delft quantum computer, they said that you are accessing our quantum computer, we cannot give it for free. Right now, we have made an MOU with them so that we are getting those two machines, 7-qubit and 5-qubit for free. Even our users will, we have to pay for them, sir. Similarly, when I had IBM hardware, it is disabled right now. Initially, we had the IBM hardware. We were able to offer 10 minutes per month for the users. But IBM changed the plan. They told that we are not going to give you for free. So we are working with them on a commercial model, how to get that platform here. So in order to pay that expense, we are asking. Otherwise, the platform will be free.
That's the reason I wanted to know why you are
Yes, yes,
pay them, right?
yes.
So before to ask the question, I have a question to the audience. How many of you have tried in real time in your mobile phone?
You have some feedback if you have tried. You can give us feedback anytime. You can just write it to us. We will keep improving the platform. In fact, Anirban sir has given us a lot of feedback. He took the platform, he tried the veto algorithm, he demonstrated his algorithm using this platform in one of the webinar, where we had some 700 participants attending at the same time. Right.
Yeah, so all of the systems have their own native gates, right? And when you run this quantum circuits on a certain quantum computer, so they change the transpiler changes all the quantum gates to their native gates,
Yes,
right?
exactly.
So when you showed your transpiled circuit, like on a superconducting quantum computer, it does not like have contain it native gates because superconducting qubits use Rx, Ry, and Rz gates,
We
right?
have RX, RY.
But like in the transpiled circuit, you should like
No, I did not use those gates in my circuit,
yeah, of
so you
course,
did not
but
see it in the transpiler.
after running
Huh.
it should have the like how did it change the C naught gates to the Rx and Ry gate, the
Okay.
exact quantum circuit that after running it how it comes like
Okay.
yeah this is
Naresh, is that something that we have in the platform?
actually IBM actually and many other AWS also is actually struggling with that. Actually, they sorry. Yes, so many people are actually struggling with that, and the transpilation, the main transpilation problem is actually like that. This all the IBM and all the guys are actually not able to transpile it optimally.
Okay. We,
So
we
so
are
we
doing
and
that. We
they
are
have
not showing it here.
yeah
The reason for that is we have put one proposal in NQM for the transpiler.
yeah
Okay. We have already built that. We do not want to show that outside now.
yeah
It is available. It's a good point to show it later on. Probably in a year down the line, we
yeah.
will make it available.
Yeah, actually, in quantum error correction and fault tolerance, the native gates actually matters a lot.
Yes, yes,
Yeah,
I
so
understand.
you need to have knowledge about native gates before running any quantum computer or quantum circuits in a quantum hardware. So
Okay.
in ion trap models, some they have their own native gates, and in superconducting qubits they have their own native gates. So
Okay.
you have to change that accordingly.
Yes, yes, you are right.
Yeah.
We'll show that. We actually have a plans of having this transpiler as a service. That's a separate product. It is already in the making. It's almost done. We haven't made it public, so that's why we are not showing everything over here. Yeah.
Uh, I just have a suggestion or a question. Like in IBM, when you transpile, when you do like this, and when you try to put a C naught between connections that are not there in the platform, as long as you can rename Q0 and Q1, they won't put swaps because that's an
Exactly.
unwanted use of swaps.
Yes.
So, I mean, if your algorithm wants your Q0 and Q1 to be, you cannot rename them if you have put other gates, then they will use swaps.
Yes.
Or else, in the case that you showed,
That
you
is a simple
actually,
case.
yeah, you actually don't need swaps there. You
Yes.
just had to call Q1 as Q2.
Yes.
That would actually reduce the errors that the transpilation.
Yes, you just need to map the names alone respectively so that it maps with that. Yes, I understand.
So, I mean, is it a plan of your future transpiler that
No,
you
it
are
is
going to?
already there.
Okay.
That's what I was telling. It is already there for a complex circuits. This is a very simple circuit, so we have introduced that. And this machine was integrated just 1 week back, this Quantum Inspire. So there are some work which is being going on.
And one last note, like when I get a faulty output, so in platforms like IBM, I can go and look at what are the errors in, like he said, like native gates, what's the percentage of its accuracy and everything I can look at. Like, can I do the same thing in Qniverse? When I get an incorrect output,
Yes.
can I characterize it properly with all the gates that I have done inside it?
Partly it is there. If you go to the job page where there is 2 tabs, output and error, the error will give you some detailed information about why the circuit was failed. You'll be able to do certain things. But the other thing, that characterization details, that is not there.
Thanks. Very nice talking.
Thank you. Okay, so you can give us feedback. We will keep improving this platform like Sandru sir told. It will be always free. And for Sandru sir's team members, it is ever free, right? So need not worry, sir. Yes. Actually, I was asking Mohit to get the photonic simulator integrated before I come for this talk. It is there. I have the slides to show that, but it is not in the platform. So you can see that this gate-based circuit is getting translated into an optic circuit. You will see how many number of optical components that makes up for making a Hadamard gate and CNOT gates, right? So that is a very good transpiler that we have done. Probably I can show it to you later on.